So far we have talked about MOS currents in the saturation, linear and cutoff region. Cutoff, we said the current was 0. We'll just modify that belief a little bit here. So we'll talk about something called a subthreshold region. Subthreshold means when VGS is less than the threshold voltage. That's what it means, subthreshold. Okay. Before that, let's just draw ID versus VGS once more. Uh, we defined a voltage, threshold voltage, below which we set the transistors in cutoff and hence the current of 0. And above threshold, the current is a square law provided VGS is greater than VGS minus VT. This region was called saturation. If VDS is less than VGS minus VT, it would have been linear current and the region would have been called linear region. Okay. Our question really is the current in the cutoff region 0? Okay. It actually exactly is not 0. It is a small quantity, but it is an exponential dependence on VGS minus VTH. It is given by ID equal to I naught e power VGS minus VTH divided by NVT, where this VT is the KT by Q voltage, a thermal voltage, 26 millivolts at 300 degrees C. N is a constant definite moment. VGS minus VTH is the excess VGS voltage above the threshold voltage. You notice that this form is almost like a bipolar current equation, where it was IS e power VBE by VT there. Here VB is replaced by VGS minus VTH. Okay. This term I naught is dependent on Cox and W by L in this format. It's mu Cox W by L VT square e power 1.8, and it will vary with process. Okay. So all you have to remember is proportional to W by L and proportional to Cox. N varies from 1.4 to 1.5. It's an empirical constant fit to make sure that the observed ID is proportional to this value. Observed ID matches this equation. Okay. Notice one thing, that we have said that ID is actually proportional to VGS, but we didn't say anything about how it depends on VDS. Right? Is it same for all VDS? Cannot be, right? Because when VDS equal to 0, no current should ideally flow. So this equation will now modify by adding this fact, multiplying by this factor 1 minus e power minus VDS by VT. So when VDS equal to 0, this term becomes 1. 1 minus 1 will give me 0. Enter ID will become 0. And VDS is a few millivolts larger than the VT, tens of millivolts larger than the VT, which is just 26 millivolts. This factor almost goes down to 0. You will get your original equation I naught e power VGS minus VTH by NVT. So this is a small modification to accommodate for variations with VDS. So for all our future discussions, we'll just confine ourselves to this portion of the equation, assuming that the VDS is at least 2x or 3x the 26 millivolts, which is not a fairly bad approximation in most of the cases. Now, we saw that the current, so I'll rewrite the form. I'll just drop the VDS minus VT, e power VDS term here, and just write it as I naught e power VGS minus VTH by NVT. We are assuming that VDS is at least 2x or 3x the VT voltage. If that is so, I will just take the logarithmic log of ID. I just take the log of the entire expression. It's log ID. Okay, is log I naught plus e power plus VGS minus VTH by NVT log E. And when you plot it, you'll see that log ID is actually proportional to VGS minus VT. Okay. So same ID versus VGS curve now I'll draw in a semi-log scale where VGS is linearly varying, but I will draw ID in a logarithmic fashion. You can see it's 1 milliampere, then 0.1 milliampere, 0.01 milliampere, which is 10 microampere, then 1 microampere. It falls by 10 times for the same range. So it is a logarithmic scale that I'm plotting here. And when you draw this, you see the current in the cutoff region is linear. It has to be because it is proportional to VGS minus VT by NVT. Right? And this region is called a subthreshold region. The slope of this curve is called a subthreshold slope. Notice that this curve looks like as if though it is saturating. It is actually not saturating. It's not the MOS characteristics where we drew before, where ID versus VDS, the current tended to saturate. This is saturating only because we've drawn it on a log scale. Ideally, this is actually a ever increasing current in going as a square of the VGS minus VTH. We've seen that before. Just the nature, since you've drawn it on the log scale, looks like as if though it is saturating. Don't get misled by that. All we are now focused here is on this linear curve. So I just rewrite this log ID is log I naught plus Vgs minus Vt by NVT log 10, ln 10. I'm just taking this NVT log E base 10 is 1 by log 10 base E, but log base E is called ln. Right? So just replace that with this and you get Vgs minus Vth divided by NVT ln 10. Right? This NVT ln 10 is called the subthreshold slope. Right? It is how many typically this is about 100 millivolts per decade. This number comes out to about 90 millivolts if you take VTS 26 millivolts and NS 1.5. And if you take a little bit different temperature or N is slightly higher, you'd end up with this. 100 millivolts per decade is a good approximation because it gives us a very good insight into what's happening. Okay. What this effectively means is if VTH scales down by 100 millivolts, you can see it here. If VTH scales down by 100 millivolts, right, this term actually increases by 100 millivolts. And 100 by 100 is about 1. And so this entire log term is now a factor of 1 addition. And what does it mean? This is base 10. That means ID has to increase by 10 times more. It's like log 10 is 1 and log 100 is 2. Right? So 2 to 1, there is just a 1 difference here. But log has to be multiplied. Since it's inside log, current is multiplied by 10 times. Right? So current actually increases 10 times. And I've called it the leakage current here because for digital folks, this current should have been ideally 0. Below VTH, when they turn off a transistor, they'll make VGS equal to 0 or small. Right? When that happens, you want your current to be 0. When VGS equal to 0, you want the current to be 0. But that doesn't happen in case the VTH is reduced. Right? So VTH is dropped by 100 millivolts. Even at VGS equal to 0, you will get a current. And that current will increase 10 times more compared to when VTH was 100 millivolts above. Right? And why does this become important? In deep submicron technologies, as the process voltages are reduced, right, you cannot scale VTH to a large amount, by a large amount. Right? Let's say the 5 volt process, we had 0.35 microns at 5 volt process, dropped down to 1.8. Now core transistors are 0.9 or even 0.8 supply voltages. Right? But VTH, if you take a look, has scaled from 350 to 400 millivolts down to about 200 millivolts. And the reason for that is if you scale VTH too much below, the leakage current, the current that the off transistor takes will increase. And you don't want that because if there are billions of transistors sitting, which are supposed to be off, but each leaking a large amount of current, you'll find very soon that the active power is much smaller than the leakage current. So leakage current is actually has been one of the biggest problem to solve in digital ASICs in the last 5 to 6 years, or maybe even 10 years. Okay. So scaling of VT is not aggressively possible, and it is because of this relationship out here. Okay. You really do want to have low VT devices so that when it's turned on, you get a lot of drive. But VT, if you reduce, your leakage current increases. Of course, only the digital people call this leakage because they really didn't want this current. Analog folks actually tend to, as I said before, can make use of this exponential relationship to make some cool circuits. So it just depends on what application the transistor is used in, that whether it is a problem or not, it depends on the application that is used in. So this is something that you'll have to remember, that VT cannot be aggressively scaled down, because if you did do that, your leakage current will increase. And this leakage current is also known as a subthreshold current. Depends on whom you talk to. Okay. Now let's take another effect. This is called the backgate effect. Okay. Backgate comes from the fact that you saw that this is a gate, and the potential of the gate impacted the channel charge, and hence impacted the amount of current conducted between the drain and source, or source to drain, depending on whether it's NMOS or PMOS. Backgate is, the substrate is called backgate because we'll see that this potential also has an influence on the channel charge. Though it's small compared to the gate, it still has an impact on the channel charge and hence the conduction. Since it has an impact on the channel charge, it's also called a gate, right? And hence called a backgate effect. In fact, some advanced advanced transistor designs later, you'll see like FinFETs and other thing, do effectively use this backgate for more advanced more advanced transistor functionalities. We'll first talk about what the backgate effect is and then come back to other thing later. So let's start with a transistor which is biased with certain amount of VGS and a certain amount of VDS. Let's say it is in saturation region. The channel is formed but is pinched off because VDS is greater than VGS minus VT. So the channel actually doesn't go up to the drain. Right? You do have some depletion region below the channel which is represented in this region out here. Let's say the source is biased with respect to the substrate at a voltage Vs. So the source is above the substrate by a voltage Vs given by this voltage Vs. Okay. The source to bulk and the drain to bulk are also PN junctions which are reverse biased, right? Because this is P type, this is N type, this is P type, this is N type. So you have a diode in this direction, diode in this direction, and since N is more than the P, it is reverse biased. Hence you get a depletion region here as well. Right? You get a depletion region inside as well, but you'll not worry about it right now. So the depletion region, the substrate consists of this area, and this area here. Okay. Now let's call Q inversion as the charge in the inversion region, Q depletion as the charge in the depletion region, and QG as the charge in the gate. And we know, right, this Q depletion, the one that we're going to use it in this particular context, is going to be that Q depletion which is mainly coming from the gate. But is also influenced by the source drain voltage. Right? Because the depletion region of the source and the drain do interact with this effect from the gate. So the depletion region here, for example, or here, for example, do get impacted by the drain potential with respect to the bulk and source potential with respect to bulk. Right? So Q depletion arbitrarily will take at some point where let's say it is in this region. Qualitatively, let's say it is only in this region. Right? These depletion region charges are purely because of the drain and the source and is not impacted by the VGS. They are too far from the VGS to get impacted by it, by the channel potential. Right? So the Q depletion will just consider those which get affected by the potential at this surface here. Right? So it will be in this region, and this region again, remember, do get impacted by the source and the drain as well. Now we know QG is equal to Q inversion plus Q depletion, and this is just the charge balance that we have before. Okay. Now, what happens now from this situation? You increase the Vs potential. All we did is let's say we increase the Vs potential. When you do that, the source voltage definitely increases. The drain voltage also increases. Right? The gate voltage also increases, but VGS is constant. VGS is absolutely constant because VGS is applied across this. Right? Drain with respect to bulk increases, source with respect to bulk increases. That means the reverse bias on these diodes increases, which means the depletion region widths will increase. Right? So what happens to the depletion region here is not much of concern for us. But since the source and drain voltage impact the depletion region charge here, right, the total amount of Q depletion charge actually is now increased. This Q depletion has now increased. But QG has remained constant because VGS is constant. QG is more defined only by the VGS value. So QG has remained constant. Okay. So Q depletion has increased, which means for a given constant QG, Q inversion has to reduce. So we increase the source voltage, which increases the depletion region charge, which actually for charge balance reasons will reduce the amount of charge in the inversion region. What does this mean? This means for the same QINV, okay, I have to get the QINV back to the same original value. I have to increase VGS. The only way is to increase QG to get QINV to the same old value because Q depletion has increased. Right? This effectively means that the VTH has increased. To get to the same QINV now, when the VS increases, I have to increase VGS, which effectively means my threshold voltage has kind of increased. Okay. This effect is known as a backgate effect. Okay. The threshold voltage increase because of the reduction in the inversion charge voltage due to the increase in the VSB voltage is known as a backgate effect. Okay. Mathematically, we modeled it as an increase in VTH. It's just a mathematical model. Remember, VTH is just an arbitrary point. Right? But it's a very convenient point for us to say, okay, VTH of the transistor has increased. Because it's very difficult to keep going on saying Q inversion has reduced. From a design parameter point of view, threshold voltage is a design parameter, and we say, okay, that has effectively increased. That impact on the threshold voltage because of VSB is known as the backgate effect. And VTH, of course, reduces the increasing VTH will reduce the current. Okay. Now, VTH is given by VTO, the original threshold voltage at zero bias, zero VSB, plus a gamma times this function, where phi f is actually the Fermi level function, depends on the doping densities of the substrate. Okay. Let's assume this is a constant for a given process. You can see it depends on the square root of VSB. So when VSB is 0, these two terms cancel out. This entire terms become 0. You get VTH equal to VTO. Right? That's what VTO effectively is. The threshold voltage on VSB is 0. But when VSB is increased, VTH will increase. This factor gamma is called the backgate coefficient and is given by Tox by epsilon naught root of 2q epsilon I epsilon of silicon times Na, where Na is the substrate doping. Tox is the gate oxide thickness. Okay. So if you increase VSB, Q depletion increases, backgate impact increases. If you increase Na, the substrate doping profile, right, again Q depletion increases. Remember we said that, right? If for a largely doped, the more the doping, more the depletion charge. Remember the PN junction, right? So if you increase Na, the Q depletion increases, backgate increases. You can see that from if you increase Na, gamma increases, the impact on VTH increases with increasing VSB. If you increase Tox, on the other hand, right, gate influence reduces. Tox is nothing but the gate oxide thickness. If the gate oxide thickness increases, the field lines from the gate has a larger distance to travel, hence its influence on the channel reduces. We've seen this before. And if that reduces, the impact of the backgate proportionally increases. This is kind of an indirect impact. So backgate effect again increases. So Tox increases the backgate impact, and you can see it here. Tox increases the gamma, which increases the backgate effect. So in deep submicron technologies where the gate actually is much thinner, Tox is much thinner, the backgate effect is not so high. Okay. So you can still play with the VT. So you do reduce it, you get, that's how you could reduce it to 200 millivolts. Right? Okay. So that's what about the backgate effect. Now let's in turn take a look at capacitances. MOS transistor capacitances. Okay. A MOS transistor cross section, I've taken an NMOS transistor, is the same for PMOS, consists of a source and a drain in a bulk, which is sitting in a bulk, in this case a P type. The source and drain are N plus, and you have an oxide and a gate. A gate and an oxide is there. Right? A typical cross section of a MOS transistor. From a capacitance perspective, we did see that the source and the drain with respect to the bulk have junction capacitances. These are the most easiest one for us to identify, no problem at all. Now for the gate, we have gate to substrate, which is a capacitance because it's we have got an oxide in between. You have a conducting plate and a conducting plate at the bottom. You get a capacitance here. You get a source to gate and a gate to drain as well. Gate to source and a gate to drain as well. Okay. We'll see all these three in a moment. We'll talk about this a bit later. So we'll talk about CGS, CGD and CGS, all the capacitances for the gate in a moment. And then later we'll talk about the reverse bias junction capacitance. This anyway you know. It is the PN junction reverse bias junction capacitance, which you already done. But we'll just look at a few geometric aspects of it. Okay. So let's just talk about CGS, CGD and CGS first in the cutoff region. Right? Because these things do tend to depend on what region the transistor is operating in. Okay. So CGB, CGS and CGD in the cutoff region. Right? In the cutoff region, what happens? Right? In the cutoff region, what happens? I'm just now giving a normal 2D cross section. There's no inversion region. Neither there is a depletion region. The substrate is as is because there's literally no voltage across the gate to substrate. So the substrate we know is doped in this case by a acceptor type because it's p-type bulk. If it was a PMOS, it will be a donor type. So it has got some conductivity. It's not a great conductivity, but some conductivity. Right? So the gate to substrate capacitance is just given by a parallel plate capacitor gate to the substrate separated by this oxide. Right? So it is Cox into WL, which is the area of the gate. W into the length is the area of the gate. So Cox per unit area capacitance into the area. This is your CGB. Right? This capacitance is not a great capacitance because it has to be contacted on the back side through a resistance element. It's a resistive element. It's not heavily doped, right? It's lightly doped. So there's going to be some resistance. But nevertheless, this is the capacitance. We'll just write the capacitance right now. Okay. What about CGS? There's nothing in the CGS here, right? Gate to source and gate to drain are nothing. There's no channel formed. So there's no contact from the backside to the source and drain. Right? So these things are 0. Okay. Now let's talk about the linear region. What happens in the linear region? You get a channel formed in the substrate. The inversion happens and then you get a channel formed. And the channel actually contacts both the source and the drain, both the sides. Okay. So now we can see the gate, all the field lines actually terminate in the inversion region, which is connected physically to the source and the drain. The substrate is actually insulated from the gate through a depletion region. We've seen that before, right? So the no field lines from the gate actually come to the substrate. Hence the capacitance is 0. The gate to substrate has now gone down to 0. Okay. CGS and CGD do have capacitance now because you have the Cox WL here fully, right? But now it is actually is connected to a resistive area. The inversion region is actually resistive, connecting the source and the drain. Okay. So how do we talk about it? So we'll think about it. The Cox WL is actually a set of distributed capacitances out here, and the channel is resistive. Okay. I've just not drawn the resistor, but it is resistive here across this region. Right? So it is wise enough for us to do one approximate model for this is to combine half the capacitance into the CGS and combine another half to the CGD, right? And then put the resistance between source and drain. That's just a modeling issue, right? So we say each one of them has half Cox WL as its capacitance. So CGS and CGD both are half Cox WL, W into L. So, okay. Now, what happens in the saturation region? When you go to the saturation region, the channel is actually pinched off from the drain side and it's connected to the source side. The amount of channel charge has somewhat reduced as well. Right? Again, CGB is almost isolated. There is a substrate, there is a depletion region here, but most of the field lines actually terminate in this depletion region. The gate to substrate still is 0. In the saturation region, gate to substrate is 0. Gate to source is 2/3 W Cox W by L. It's not just full Cox W by L, it does reduce because the inversion region charges have reduced. And the CGD still is 0 because the channel doesn't connect to the drain. There's not much of capacitance out here. There's a depletion region which is very small. We'll put it as 0. Right? So this is in a way a good approximation of the capacitance. These are useful for hand calculations and good and gives decent results. Okay. Now, just before we go to the PN junction diodes, the drain to bulk and the drain to source, there's one small thing that we need to cover, which is called the capacitance switch overlap. These regions here, right, the gate to drain and the gate to source, though we are drawn perfectly ideal that they're fully aligned, they're usually not. Right? So if you go expand this region and see, the gate actually overlaps the source and drain region by a small amount. And this happens because the way the source and drain are implanted and annealed. So you do implant around this region here, and then when you thermally anneal it through the process, some amount of diffusion of the source drain material happens into the substrate, and a small overlap region does come about. So when you have a gate to source drain overlap like this is a good connector, this is also a good connector, you do get a small capacitance here. right? That is called the overlap capacitance, right? You also have a gate sidewall which is actually facing the source drain, right? You do get a fringe capacitance. Especially if the gate oxide thickness is small, the fringe capacitance can be large, right? Both together we're going to call them as overlap capacitance. It's difficult to isolate one from the other, so we call the uh, overlap capacitance, right? So all the time where we have put, because there is no gate to source overlap, it's zero. All these will now get converted to a C overlap capacitance, right? That's all it is, right? So CGS and CGT, these are capacitance overlap capacitance, and this typically is determined by the process. Of course, it depends on the W, doesn't depend on the L. If you notice, L is this geometry, right? And that's a design parameter. That capacitance doesn't depend on L, but it depends on this amount of overlap capacitance here. Hence, it depends on W for sure, right? Because more the width, the more the overlap capacitance. But more the length has no impact. More or less the length has no impact, because this distance is not governed by the length at all. Okay. Okay, let's now turn our attention to the sidewall capacitance, the two PN junctions that we talked about. Right. They're all reverse bias, so no problem at all. I'm just drawing a cross section of the gate, the oxide, and one of the source and drain, just to show you where we are. It's a geometric problem, because we know how a reverse bias junction capacitance works. It is proportional to 1 by root V, and is proportional to the doping concentrations and other thing. Okay. The width of the gate, let it be W. The length of the implant, the source drain implant, not the length of the channel. Length of the source drain implant is L substrate XD, and let the junction have a depth of XJ. Okay. So I'm just drawing the physical attributes of the source drain, right? Junctions itself. We'll just remove the source drain, the gate oxide, and we can see now this width W, length is LSD, and junction depth is XJ. Okay. Now this region has 6 faces, one on the top, one at the bottom, and 4 on the sides. And we'll study each one of them. On the top, really has no capacitance, because it's facing the air side. Air has no conduction, so the top wall actually doesn't give you any capacitance. Okay. The bottom wall, the more highlighted one here, actually has a capacitance. Okay. The side wall also has a capacitance, right? Because they're all facing the substrate in a way. Okay. This side wall we'll not talk about, because it is actually part of the transistor itself. We'll talk about it actually a bit later. Okay. So just take a look at the bottom wall capacitance. Bottom wall capacitance is a capacitance because of the bottom wall. Okay. Bottom wall area is W into LSD. Very simple. There's nothing more to it. W into LSD. Okay. So the net effective capacitance is the capacitance at 0 voltage into W into LSD. Nothing but capacitance per unit area into the area, where CJO is the net capacitance at 0 voltage. Now, of course, you have to adjust this for the source to bulk voltage later, or drain to bulk voltage. So you'll have to multiply it by 1 by square root of VSB. So CJO is 0 bias bottom plate capacitance junction, which actually will reduce with this is just at 0 bias. So at any other given bias, you know how to calculate that. Sidewall, what happens to the sidewall? Sidewall has 3 areas, 3 faces. This face and this face have an area of LSD into XJ, and this face has W into XJ as its area. Okay. So the total area is W plus 2 LSD into XJ, where XJ is the depth of the junction from the in the substrate. Okay. So the net junction sidewall capacitance is junction sidewall capacitance at 0 bias times the area. Okay. Which can then be written as C prime junction sidewall capacitance at 0 bias into the perimeter of the 3 sides, and where C prime JSW is nothing but C JSWO into XJ. I'm just replacing by that. And the reason why we're doing it is XJ is actually a process parameter. The designers have no control over it. Then the designers have control on W and LSD. Right? So CJSWO into XJ is called C prime JSWO, which is nothing but zero bias per unit length now. It's not per unit area because you're multiplied by the depth already. It's per unit length cap of the sidewall. Okay? So if the perimeter increases, you just have to multiply this by the perimeter. This factor by the perimeter. In this case, the perimeter is W plus 2 times LSD. Right? Remember, we just removed the XJ factor out because it's a process parameter and you really don't have control over it. Okay? So we put a new thing which is capacitance per unit length of the sidewall. Okay. What about this capacitance? This capacitance actually is incorporated in the MOS transistor itself. Okay, and it's not considered because as part of the MOS transistor, because this is part of this phase actually touches the channel. The channel capacitance, the CGB, CGS is there. That it gets accounted there itself as part of the MOS transistor itself. So its capacitance is definitely there. Right? It's not because the channel is really at the surface. This capacitance definitely is there. It is facing a depletion region side below it and touching the channel at the surface. This capacitance definitely is there, but it is embedded in the MOS transistor itself. When they extract the MOS transistor, they will embed this capacitance in the equations of the MOS transistor itself, the parameters of the MOS transistor. So if you do take a SPICE netlist, you will see the bottom wall area and the three side walls that we talked about. The top anyway doesn't contribute, but you will not see this particular junction area being accounted for. Because the designer, as we again said, has no control over it. It is always going to be there. Whether you like it or not, it's going to be there. So it is taken as part of the MOS transistor. Okay. So with this, we kind of conclude the capacitance of a MOS transistor as well. Okay. The inner wall capacitance is observed